How's everyone doing today? You enjoying your DevOps? Show of hands, who's loving DevOps? Nice. You can woo too. Wooing's fine. Wooing's fine. As we're giving people a few moments to come in the room here, I think I'll just start with kind of the motivation behind why I created this presentation, because I think this is very important, like a key part of the value of this presentation. So as I was looking for explanations of what this deep learning stuff was several years ago when I first heard about it, I really struggled to find good information about what deep learning was. I found typically one of two things. Either extremely fluffy marketing speak that sounded more like magic than actual technology, on one hand, and then on the other hand, I found overly complex, highly academic content that required understanding of both calculus and linear algebra just to understand the concepts. And now I had the background in calculus and linear algebra, so I could understand what they were explaining, but there really was nothing in between. Nothing for people that didn't have a strong background in math and statistics, but needed to understand what this deep learning stuff was so they could figure out, is this even something I should be looking at, or is this something I should be applying at my job, or where do I even go to get started with it? So this presentation essentially is trying to hit that sweet spot in between. I'm hoping it's not so high level it just sounds like fluffy marketing speak, but it's also not going to require all of the calculus and linear algebra just to understand the basic concepts. All right. So, quick show of hands. How many of you are in the same position that I was in, and you're like, I've heard this word deep learning, I have no idea what it is, I'm here to figure this out today? Okay, that's a good chunk of hands, no problem at all. We're going to answer that. And how many of you kind of know what this deep learning stuff might be or is, and you're just trying to figure out, is this something I should be using in my day-to-day job? Okay? All right. And how many of you are trying to figure out, well, where do I just go to get started? I want to get moving with this stuff. A few people? Okay. So that's essentially what we're going to be focusing on here today, trying to answer those three questions. So whether you realize it or not, our world is going through a major transition as we speak. We are entering the era of artificial intelligence and machine learning, a future where machines are going to be doing many of the jobs that human beings were once doing. And as a result, the software industry is also going through a significant transition as well. So in the past, we'd have to explicitly program a computer step by step to get it to solve a problem. This involved a lot of if-then statements, a lot of for loops, and a lot of logical operations. In the future, however, machines are going to teach themselves how to solve problems on their own. We just have to provide the data. And now, this is a radically different way of working with a computer than we're used to as software developers and IT professionals. While there's a growing demand for individuals with the skills necessary to implement machine learning, there's currently a shortage of people capable of teaching machines how to learn on their own. As a result, those with the skills necessary to teach machines are commanding significantly higher salaries in the software industry, and there doesn't seem to be any end to this trend in sight. The purpose of this presentation is to introduce you to this new way of teaching a computer how to solve a problem on its own without having to explicitly program it to do so. We're going to do this by answering the following three questions. First, what is deep learning? What can deep learning do for me? And how do I get started with deep learning? So first, what is deep learning? So deep learning, as I mentioned, is a difficult concept to teach to a wide audience. It's either too fluffy or it's too in-depth and technical or academic in order to make it easy to understand. So we're going to start with what will seem like a super long definition, but then we're going to break everything down to make it much more easy to digest. We'll explain each of those parts, and we're going to skip all the complex math. We just want to get to the core of what this thing is as quick as possible. All right, so the super complicated, overly technical definition of deep learning, which we'll break down, is deep learning is a form of artificial intelligence that uses a type of machine learning called an artificial neural network with multiple hidden layers that learns hierarchical representations of the underlying data in order to make predictions given new data. So now, if you were to approach this in an article, you'd probably be like, okay, that makes no sense to me whatsoever, and you might just move on to another source of information to try finding the Deep Learning for Dummies or something guide. But we're going to take this and break it down step by step so we can understand what each of these things means so that hopefully we'll have a really strong grasp on what deep learning means at kind of the core level. Make this easier to digest. Okay, so first, let's see how artificial intelligence, machine learning, and deep learning are all related to one another. So as we can see, deep learning is a type of machine learning, which is a type of artificial intelligence. So what is artificial intelligence? Essentially, artificial intelligence is a field in computer science that attempts to create machines that act rationally in response to their environment. And this can be done using a variety of different methods. First, we can do this with explicit programming. This is where we understand step by step the problem that we're trying to solve, and we code a solution to it. We've been doing this for years. Second, we can do something called domain knowledge encoding, or what's called an expert system. We essentially encode a series of rules in a database, and then inferences that can be made from those rules. And then we use an inference engine in order to extrapolate knowledge from those rules to new information based upon that set of facts. Or we can teach a machine by identifying statistical patterns in data. This is generally what we refer to as machine learning. So machine learning is a type of artificial intelligence where we teach a machine how to solve a problem without explicitly programming it to do so. We do it by teaching the machines by example using data. So machine learning, in essence, is the application of statistics to the problem of artificial intelligence. We're teaching machines how to solve problems by identifying statistical patterns in data. Essentially, with machine learning, we use existing data in order to learn a function that can then be used to make a prediction given new data. And I assume most of you remember the term function from high school algebra. Essentially, a function is any mapping from an input to an output of some kind. So essentially, we're using data to create this function that we can then use to make predictions given new data. For example, imagine we wanted to create a function to determine whether an image contained a picture of a cat or not. The first thing we need to do is create a data set that contains a set of images with cats and a set of images without cats. We'd have a human being label each of these photos, indicating whether that image contains a cat or something else. Then we would apply a machine learning training algorithm to that data set of images with and without cats. The training algorithm would essentially produce a function that we can then use to make new predictions. Essentially, the training algorithm is learning a function. It's essentially learning what it is about an image that contains a cat that corresponds to catness. It's essentially learning catness, if you will. Finally, if we've done everything correctly, we should be able to feed that function new data, a new image it's never seen before, and it should be able to then predict or tell us how likely it is that that new image contains a picture of a cat. And now, while this is a vastly oversimplified explanation of machine learning, it essentially captures the essence of what it is that we're attempting to do. Now, there are a bunch of machine learning techniques and algorithms in existence. We have machine learning algorithms for classification, regression, clustering, and many more than we could possibly cover in an hour or even a month in a course on this. However, in order to understand deep learning, we just need to understand a specific type of machine learning called a neural network. An artificial neural network, or neural network for short, is a machine learning algorithm based on a very crude approximation of the way we used to believe the neurons in a human brain worked, or an animal brain worked. So I say it's based on a crude approximation because we now know that it's actually quite a bit more complicated than this, but the mathematical model is actually quite useful. It works really well for solving a series of problems. So we start with a biological neural network, we start with a biological neuron, which is the building block of a brain. However, we model this artificial neuron mathematically. Each neuron is modeled as a set of inputs that are coming into the neuron and a set of outputs leading to other neurons. Each neuron receives an input value from its predecessor neurons, these connections coming in, and then the values are essentially all summed in the first half of the neuron. The neuron also contains something called an activation function, which changes the behavior of the output. So given a certain input, how much should we be outputting on that neuron? Each of these connections coming into the neuron contains something called a weight, and the weight can be adjusted in order to change how the data is coming into the neuron, how much information is coming in, or how much or how little information is coming in. And there's also an additional weight here called a bias. This bias essentially just shifts this activation function either to the left or to the right, once again changing the behavior, how it's firing based upon the input that's coming into it. So each of these weights is essentially like a knob that can be tuned to change the behavior of the neuron. So by tuning all of these knobs, essentially, we're changing the overall way data is flowing through this neural network. And I should probably point out that it's essentially just numbers coming into each of these values and numbers coming out of each of these neurons. So we represent this conceptual neuron mathematically so that we can use it in a computational model. But don't worry, we don't need to understand all of this complex math in order to get to the essence of what it is that deep learning is doing. Then we wire up this network of neurons into a graph containing edges and nodes. These artificial neural networks are composed of an input layer, which you can see over here, and an output layer over here. So data flows into the input layer and comes out of the output layer. This would be our prediction, either like a yes here and a no here, or true here, false here, or you can also have multiple categories coming out, like cat, dog, and squirrel, something like that. And then we also have one or more hidden layers here in between of neurons. There's two main steps in this training process for a neural network. We have something called the forward propagation step, where we essentially just feed the data in, and based upon how these weights are currently set, we make a prediction. Is this a yes or is this a no, based upon all the data that we're seeing? And initially it's going to make really terrible predictions because we haven't trained the network up. But that error is important because every time we see an error or a correct answer, we can then adjust the weights of this network using a step called backpropagation. So essentially, if we see an error, we can tune certain things stronger and certain things weaker in order to try getting it to make better predictions with each attempt. We call this iterations, or epochs. So we do this for each sample in the training data set, and then when we're finished, we should have a neural network that's essentially tuned to make really good predictions. It's essentially using all of that training data in order to improve its overall prediction capabilities. However, because we're working with computers rather than a biological brain, we use much more computationally efficient data structures. We use things like vectors, matrices, and tensors. In fact, how many of you have heard of TensorFlow? Okay, they do a really good job with marketing. So TensorFlow is actually a really great name. Essentially, what it's doing is it's modeling a computational graph as a series of tensors, which are essentially multidimensional vectors or multidimensional arrays. So TensorFlow essentially is the perfect name for exactly what it's doing. Modeling that computational flow or computational graph using tensors as its underlying data structure. All right, so a deep neural network then is a neural network with more than one hidden layer. Adding more hidden layers essentially allows us to model much more complex functions than a simple single-layer neural network. For example, if we wanted to teach a neural network how to detect faces, we'd first feed in a data set of images with a person's face and that person's name so that we can map the face to the name. Now, in the lower layers of this deep neural network, it's going to extract geometric primitives, things like horizontal lines, vertical lines, and diagonal lines. As we get further up into this neural network, the middle layers are going to start detecting more complex facial features, eyes, nose, and mouth. And then when we get further up into the network to the upper layers, we'll start detecting entire facial features, things like the shape of a male face versus a female face, faces with beards and faces without beards, stuff like that. And at the highest level of this neural network, essentially the output layer, we have the most abstract representation of a person, which would essentially be that person's name that we're attempting to predict. And I should note that this is just an oversimplified version. There would typically be many more layers in here and much more complex interactions between the neurons than what I'm showing. And we'll talk a little bit about that later. All right, so each subsequent layer learns to extract additionally more abstract features from the preceding layer. As a result, we have what's called hierarchical representation of the underlying data. We're essentially learning a hierarchical representation that gets more abstract the further up the network we go. All right, so now let's return to our original definition of of deep learning to see if this makes a bit more sense to us now. So, as we said, deep learning is a form of artificial intelligence that uses a type of machine learning called an artificial neural network with multiple hidden layers in an attempt to learn hierarchical representations of the underlying data in order to make predictions given new data. So now, if I've done my job correctly, this should make a lot more sense to you than probably most of the articles you've seen on this topic, because to be completely honest, most of them don't approach it in a very simple way. So a show of hands, how many of you this made sense? This was a very clear explanation. Okay, that's actually very good. That's what I like to see. All right. So the earliest neural networks, called perceptrons, have been around since 1957. So these things have been around for so long. Why did it take us so long to get to this deep learning stuff? It's like, well, we just add a couple more layers to the network. It seems like that should be a pretty obvious thing. But it's taken us almost 60 years to get from the original single-layer perceptrons all the way up to deep learning. So what has changed? Well, three trends are really driving the emergence of deep learning. First, we now have lots of data. We also have more powerful computers, and we've had several breakthroughs in machine learning algorithms that have really increased their power and functionality. First, we now live in the era of big data. Deep neural networks require tremendous amounts of data in order to train them properly, and we now have tremendous amounts of data available. We didn't have that in the past. In fact, if you look at the rate at which we're increasing digital information, the amount of digital information in the world now grows at a rate where it doubles almost every 2 years. So essentially, in the past 2 years, we have created more data than the entire rest of human history. Second, we now have more powerful computers, much faster CPUs, more memory, and solid-state hard drives. In addition, we also have access to distributed computing technologies that allow us to spread out the data and the processing amongst multiple machines. Third, we've also had a series of breakthroughs in machine learning or deep learning algorithms. These have significantly increased the overall power of deep learning and neural networks. In addition, we're now able to use GPUs, the graphical processing units in our computer, in order to train these neural networks. And there's new things coming as well, too. We've got things called TPUs, which are TensorFlow processing units, FPGAs, specifically designed for deep learning as well, and other things on the horizon as well, like neural computing, essentially computers that are designed like a hardware-based neural network or designed to optimize neural network computations. But with these GPU operations, they're essentially the exact same type of operations mathematically that you do to compute a video game, the graphics of a video game, all the same types of matrix operations. So to be completely honest, we really do have gamers to thank for some of the biggest breakthroughs we've seen in artificial intelligence and deep learning in the past few years, which is actually quite interesting. All right, so now let's address the question, what can deep learning do for you? Well, quite a lot, actually. With deep learning, we can actually take a series of inputs, things like tabular data, text, images, audio, and video, and map it to a variety of outputs, predictions that it's making, which can either be tabular data outputs, like yes or no, true, false, cat, dog, cow, or pig. Text documents, we can map it to images, audio, video, and more. So we're going to go through a few of these different types of combinations, the different mappings from inputs to outputs, the functions that we're creating. So we'll start with basic tabular data, categorical and numeric values, just to see what kind of things we can do with tabular data. So first, deep neural networks can do something called classification with tabular data. Classification is essentially making a prediction that involves 2 or more categories. So either we're predicting true or false, yes or no, cat, dog, or cow, or whether a person has cancer or not. Pretty much anything you can map to a categorical output. Another example would be whether we should accept or reject a person's loan based upon all of their financial history. Second, deep neural networks can perform regression on tabular data. Regression is attempting to predict a numeric value as output. So, for example, if we had a bunch of houses and we're trying to figure out how much a house is likely to sell for, we feed in all of the feature data and all of the previous sales prices of houses that are similar, and then we feed in a new house and all of its property, or all of its attributes, and determine how much that house is likely to sell for based upon all of the previous data. So next, we can use text documents as input to deep learning algorithms as well. For example, we can perform document classification where we attempt to predict which category a document belongs to. For example, trying to predict whether an article is technology, sports, or entertainment. We can also use deep neural networks in order to generate text as well. So, for example, we can feed the the body of an article into a deep learning algorithm and then have it produce a potential headline for that article. As you can see, each of these headlines that was generated by this deep learning algorithm essentially reads just like an article headline that a human being would come up with. It really does do a great job of capturing the essence of that article and even seems to play on human emotion. Essentially, it uses certain terms that essentially would draw a person into reading an article. Now, we can also use images as input for deep learning algorithms. So, with images, we can do certain things like gender classification, age regression, emotion detection, and object recognition as well. We can also do other things like image segmentation, where we take a complex scene and then we have the algorithm essentially determine which pixels belong to which object, and in this case, we're specifically color coding each of those objects with a corresponding color. We can also perform image captioning, where we describe what's happening in an image using a deep learning algorithm. So, for example, the deep learning algorithm takes this image as input and then essentially spits out a description of what it thinks is happening in that image. And, I mean, if you read these, this is pretty accurate. I mean, a human being would produce pretty much the same response in most of these cases. However, even cooler is that we can also generate images now with deep learning algorithms. So we can feed data into it and produce an image as output. In this case, we'll feed it in an image of me and see what it predicts I'll look like 20 years from now. And so if you guys have ever seen my dad, you'll actually know that this is actually quite accurate. I mean, that really does just look like my dad. So it's even so good that it was able to trick the age detection algorithm I used on the previous slide into thinking that I was exactly 20 years older than I was when this photo was taken, which I think is actually pretty impressive. But we can also use these deep learning algorithms to generate entirely new images from scratch. So this new Rembrandt is essentially created by a deep learning algorithm that learned how to paint in the style of Rembrandt. It looked at all of Rembrandt's previous works and then essentially learned what it was about painting that was uniquely Rembrandt. It painted this new image. They showed it to experts. They're like, yeah, we would have thought this was a Rembrandt had you not told us a computer painted this. And it's actually kind of crazy. And these imaginary celebrities are essentially, they all look like people you've probably seen before, but not a single one of them is real. Each of these was generated by a deep learning celebrity generator that was trained on, I think, 200,000 high-resolution images of real celebrities. So its job is essentially to produce fake celebrities that look like real celebrities. In fact, we can even watch this algorithm as it's progressively learning how to generate more and more celebrities or more and more complex celebrities over time. And you can see its resolution is increasing as it becomes better. And so it's essentially just, all it does all day long is spit out new celebrities that look like people we know, but not a single one of them is real. Yeah, isn't that crazy? And this is all stuff that's just come out in like the last year or two. So this is moving really fast. Even cooler than that, in my opinion, is they're working on prototypes to use deep learning algorithms to do text-to-image translation, if you want to call it that. So what we do is we feed in the text of what image we want the computer to produce, and it essentially spits out what it thinks matches that. So this isn't actually doing like an image lookup in a database. It's essentially synthesizing a new image based upon every image it's seen in the past and all of the textual labels that were associated with that image. And it's actually getting pretty good at this. It's literally going to be to the point in a couple of years where you will just tell the computer, oh, I need an image of this for my presentation. And it's going to just generate the image for your background for your slide. Or even better, you just feed in your slide deck, all of the notes, and it's just going to produce the appropriate slide for each topic you're talking about. And now we can also use audio as input for deep learning. So, for example, we can perform speech-to-text translation now with near human accuracy. In fact, I think they may have just beaten it this year. I can't remember. But if they haven't beaten human-level recognition, it's coming within the next year. It's very close right now. But we can also generate audio as an output with deep learning as well. For example, we now have deep learning speech synthesis that is almost indistinguishable from human speech. I assume several of you have probably heard the whole Google robocall thing. It's apparently generating a lot of buzz on the internet. If you guys have heard that, this probably isn't as impressive because this is essentially the voice, that same voice.
A single wavenet can capture the characteristics of many different speakers with equal fidelity.
So,
now, it's fast.
Sorry, I have to wait for the robots now. You can still tell that there's certain things in the inflection that don't fully sound human, but it's getting really close to the point where the average person listening to this on the phone is not going to know that they're talking to a robot. They're just going to assume they're talking to another human who just has kind of weird vocal inflections, I guess. And I think even cooler than that is that we're on the verge of having applications that allow us to essentially modify human speech as if it were just a text document. So this is a new project that is being created by Adobe. I can't think of the Project Voco is the name of it, or is the working title of it. It essentially allows you to feed in audio, human speaking, some narration. It then does transcription, so it gives you the text of what's being said, kind of in place with those words as they're being said, and then allows you to go in and edit the text just like a word processor, and then you click a button and it essentially produces the audio, that person's voice saying exactly what you wanted it to say. And now, while this isn't perfect yet, I'll let you hear a sample of what, not this project, but something similar to it does with my voice.
Hello, my name is Matthew Renze.
So while it still sounds like a computer speaking in my voice, it definitely has the vocal characteristics of my own voice in there. So I'm hoping in the very near future, I create courses for like Pluralsight and DataCamp. And if you make a little mistake and you're on the road, you have to wait until you're back home in your recording studio to get the ideal like recording environment to make that 1 or 2 word change. So in the future, I'm hoping just to be able to, while I'm on the road, just make these little modifications, and it's going to spit out good enough audio that I'll essentially be able to make these like minor tweaks to my courses online. And that's a huge thing for someone like me that spends most of my time on the road. So we can also use video as input for deep learning algorithms now. And this allows us to do some really cool things like real-time object motion tracking, object detection, and facial recognition. And this is a project called YOLO. These guys are kind of pushing the envelope with real-time image tracking these days, or image analysis. So you can imagine all of the applications something like this is going to have, just being able to do real-time object detection, face detection, and probably some privacy and security concerns as well, too. Even cooler than that, in my opinion, is that we can now generate video with these deep learning algorithms. In fact, the following videos are completely synthetic. They are former President Barack Obama, based on hundreds of hours of his previous videos of public addresses. So this is created by a lip-syncing deep learning algorithm that essentially used those videos in order to come up with a model for how he speaks visually. And so the only real input here is essentially an audio from another speech that he gave that is not being shown.
To help families refinance their homes, to invest in things like high-tech manufacturing, clean energy, and the infrastructure that creates good new jobs.
So you can see how potentially dangerous this technology is going to be if society is not prepared for this. And right now, society is not prepared for this. You could take a video of a president and get him to say something that he never actually said, and the majority of all people on the planet are going to believe this because we are very susceptible to fake news. So we really do need to be waking up to the fact that these technologies are here and that we need to be responsible for what we're doing with these technologies as well. Okay, on a much lighter note, you can also have fun with these algorithms. This deep learning algorithm was tuned to see only dogs, so it's designed to detect only dogs. So everything it sees is some form of dog. It's just a person going through a supermarket with their camera, but the algorithm, when it's essentially trying to do detection, is just seeing everything as some kind of dog. It is literally hallucinating dogs in like the most real sense of the term. We'll just stick with this here for a second or two. It's super trippy. All right. So, but this is just the beginning. So these are just kind of the basic, audio, video, image inputs and outputs. But with deep learning, we can take a variety of different types of inputs and connect it to a variety of different outputs. In addition, we can combine multiple inputs and produce multiple outputs as well. And that's going to lead to some pretty new innovations or interesting innovations. For example, self-driving cars, we essentially connect a variety of sensor inputs to a set of vehicle control outputs, and we're able to drive a car fully autonomous without any human intervention. In addition, people have been trying to use these deep learning technologies to get artificial bodies to walk in simulated environments. And once you can get an artificial body to walk in a simulated environment, you're a pretty large step closer to getting a real robot to walk in a real environment. And I should probably note that this is really early on in the training iterations. This thing has gotten so good at walking that you can like throw boulders at it and it will just like, and it just walks right around. It's really impressive now. In fact, this thing could walk better than I can, I bet. Except there, he's dead. All right. And, I mean, all of this stuff is essentially leading to things like this. Oh, I think I have to hit the button once more. I mean, seriously, how many of you can do that? All right. So, while I need to point out, though, that robot that you just saw was not done with deep learning technologies. That was all done with explicit programming. So while this deep learning stuff is super cool and is going to be quite revolutionary, there's still a lot of value in explicit programming, and it's going to be around for quite a while. until program synthesis essentially puts us all out of jobs. We'll talk about program synthesis another day. Maybe that'll be a keynote next year. That's essentially where we use deep learning algorithms in order to generate code to solve problems, but whole nother story. All right, so to kind of break things up, just to keep things interesting, these deep learning algorithms, as we've seen, are really good at detecting things in images, but they sometimes struggle with certain types of images. So we're going to play a little fun game here called Dog or Mop, where we essentially learn what types of objects these deep learning algorithms have difficulty detecting right now. Here's how it's going to work. I'm going to show you a picture, and you're just going to tell me whether you think it's a dog or a mop. It'll start out easy, but it'll get a bit more difficult. Okay, first picture, dog or mop? Dog, that is a dog, correct. Okay, next picture, dog or mop? Yes, you were right, that is a mop. How about this one, dog or mop? I hear some mixed opinions here. Let's see what the video says. Oh, that's a dog. Okay, but you can see why a machine might mistake that as a mop. I mean, it makes sense. What about this? Dog or mop? That is a mop shaped as a dog. How about this one? That is a dog inside of a mop. And it's not just dogs and mops that these algorithms get confused. They also confuse other classes of objects that surprisingly have to do with dogs quite often. So we can play games like Beagle or Bagel, and we can also play games like Chihuahua or Muffin. In fact, there's whole internet memes just on misclassifications with deep learning algorithms now. A lot of fun. Okay, so how do we get started if we want to learn how to use deep learning in our organizations? So this is a place where there really isn't a whole lot of information available on the internet or various courses. So there's essentially 3 paths that I have identified depending upon what you're trying to accomplish and what your skill level is or your level of background. We're going to start with the quickest, easiest, and the least expensive of these options and work our way to the most time-consuming, complex, and expensive option. So option number 1 is what I think I and most other people are just referring to as deep learning as a service. So this first option has essentially a third party that owns the algorithm. They essentially own the data, or they have the data, and they have the machine learning function, essentially the prediction algorithm, all trained up. So you essentially use their API with your new data in order to make a prediction with their models. Now, there are a lot of third-party deep learning service providers available. We've got Google's Cloud AI services, Amazon's AI services on AWS, Microsoft Cognitive Services, and IBM's Watson. Now, these APIs allow developers to essentially leverage existing deep learning models to add artificial intelligence to their own applications. On the plus side, this option is simple. Essentially, you just need to be able to call a simple REST API, and you can essentially be using deep learning in a day. They're quick. It only takes a couple lines of code to get one of these things up and running, and they're inexpensive. The transactions literally cost fractions of a cent to use. On the downside, these models are relatively narrow. They're designed to solve very specific problems very well, but they don't generalize well to new problems that you haven't seen before. They're remote, so you need to deal with things like fault tolerance and network latency. And they're pay-per-use, so as your usage goes up, your Azure bill is going to go up as well. Option number 2 is what I'm tentatively calling as deep learning as a platform, because there really aren't good established terms for these things yet. And this is getting a little blurry as well, too, as to what this exactly means. So with the second option, a third party is providing the algorithm, you're providing the data, and then you use your data with their algorithm to create a custom model that they then host for you in the cloud. There's not a whole lot of these options available right now, but I'm seeing them emerge, and I think this is a space that's just going to explode in the next few years as people figure out how to make this, I don't know what the right word is for it, but make it easy for people to just get their data into these systems and get the predictions made. So right now, the 2 big ones that I'm aware of are Azure Azure ML Studio, and Microsoft Cognitive Services has 2 custom services, a custom vision service where you can detect your own objects or your own business logos or something like that, and a custom speech service where you can train it to detect words in a specific vocabulary. Say, for example, you're in the medical industry. Those terms are not going to be well recognized by a general speech service because certain words just don't exist in normal language, but are used heavily in the medical industry. So we'll take a look at 2 of those during our demo here at the end. Now, on the plus side, these services are still relatively simple. You just need to provide it with labeled training data, you push a button to build the model, and then you call the API to get your new predictions. They're relatively quick. Once you've got a training data set, you can train one of these models in under an hour. In fact, I'll show you do it. We'll do it here. It'll be super fast. And they're still relatively inexpensive. You've got to now spend money on training your model in their service and for each prediction on a per prediction basis, but this is still relatively inexpensive. On the downside, this requires training. So you need to provide the model with your labeled training data in order to teach it how to make new predictions. It's still remote, so you're still going to have to deal with things like fault tolerance and network latency, and it's still pay-per-use. But now you're paying for both the training time and for the per transaction cost, each prediction. Option number 3 is the do-it-yourself option. So with option number 3, you create your own algorithm, you provide the data, and then you use your algorithm with your data in order to create a custom model that then you host yourself. Fortunately, we now have a lot of really good open source deep learning frameworks that allow anyone to create their own deep learning models. The industry got really smart and decided to open source this. It all about happened in 1 month. All of these companies decided we're just going to open source this stuff because everyone needs to have access to this in order to level the playing field. Otherwise, we're going to have a couple companies that have way too much power relative to everyone else. So we've now got Google's TensorFlow, we have Microsoft Cognitive Toolkit, Torch, and Theano, but I think Theano has been deprecated. So there's a whole bunch of others out there and a bunch of newcomers as well. Like I use MXNet all the time myself. But TensorFlow is by far the most popular, and they've done the best job at marketing as well. So on the plus side, these services are completely custom. You can train your model with your own data and tune it exactly as you like. They're local, so you can host these things on premises, in the cloud, or embed your model right in your application. And they're private, so if you have sensitive customer data, the data never has to leave your data center. The downsides are that it's complex. So building these algorithms, preparing the data, and training a deep learning model is not an easy task. It requires quite a bit of effort and knowledge and experience in order to do it. They're also very labor intensive. It takes a lot of time to train and create models, to prep your data and to tune the model. And it's expensive. Of all the options, this one's going to cost you the most if you have to build something from scratch rather than reuse something that someone else has already created for you. All right, so my general recommendations are to essentially use option number 1 for the narrow, well-defined use cases. Things you'll encounter like basic image recognition, basic speech recognition, and doing things like sentiment analysis. Use option number 2 for custom use cases. These are things that fall just outside of the space of normal kind of common usage cases. So for example, training a model with your company's own data. If you need to detect your company's logo in an image, a general purpose classifier is not going to know that what your logo is versus something else. So you're going to have to train something with a process called transfer learning for one of these custom services to get that to work. And doing speech recognition in a domain-specific vocabulary. Like if you're in the oil and gas industry, your vocabulary is going to be different than the rest of the world, so you'll need a custom classifier. And then use option number 3 if option number 1 or option number 2 fail. And it'll fail for certain cases. So, for example, if you have sensitive data that cannot be moved into the cloud, you have to keep it in your data center, that would be one of the cases you'd want to do this. If the transaction costs are going to be too high at scale because you're processing every frame of video in real time, that's probably going to be cost prohibitive to send that data, each frame to the cloud and then process it. Or if you're going to be building a brand new model that no one has ever built before to solve a problem that no one else has solved before. These cases all would work really well with option number 3. All right, so now just to give you kind of a little hands-on look at what this actually looks like in real life, we're going to do a quick code demo. And unfortunately, we've got a pretty decent amount of time here, so we'll see how far we can get. I just need about 5 minutes to wrap things up and then maybe another 5 minutes for questions, so we'll just spend about 5 minutes doing this too. All right, so first things first. So with option number 1, where we're using these kind of general purpose deep learning algorithms, I'm just going to show you what this looks like. Now, typically we would be working with an API. I'm just going to be showing you a web-based front-end sample. So if we want to do image classification or detect a bunch of properties from an image, we'll feed it a new image, which will just be a picture of me. Where is it at? Oops, I clicked the wrong button. That's why. All right, so we'll send that headshot in, and we'll submit. And then you can see on the side here, it's going to begin recognizing things. So it sees that it's a person, man, indoor, building, front, I'm smiling. We've got the confidence of each of these things. So this is the statistical likelihood that I am a person and that I am a man. So that's relatively high. That's kind of cool. We can see that I am not adult content. And by adult content, we mean adult content, not that I'm an adult or a child. And then a score on that, I'm not very racy at all. We've got other things here like the face is a gender male, and then dominant colors, blah, blah, blah. So there's a whole bunch of information, and this is just a subset of all the information that we could get. We can get things like, it used to tell you all the emotional stuff, but they must have pulled that out into a separate API. It would tell you that the person was happy, whether they were sad, all these different attributes about the person's face. Okay, so that's the general purpose stuff. Here's a custom classifier. So I've got two little samples that I created. This is my buddy Corey House. So I built a Corey House and a Matthew Renze detector because we were both at a conference one day, and I thought he would find it was funny. So these are pictures of my buddy Corey House. We'll filter those out so you can see there's Corey, and here's me. And we want to essentially build a image classifier that detects us. And so we go through and we can train the model. It's going to tell us a bunch of things about the, its overall predictive power. And then I'll just use the quick test button here rather than the way you'd normally use it, which would be API calls. And then we'll grab an image it's never seen before, which is that same headshot that I used in the previous service. And it will then give us the likelihood, the probability that this is me versus Corey House. And as you can see, this is pretty accurate in terms of its ability to predict us. And you could do this with every person in your company if you needed to have the front door greeter system know who walked in the building or who didn't or something like that. So there's a lot of use cases for this kind of stuff. But it's important to note that you'd typically be using it with an API, set of API calls. And I'll just show you, the documentation for this stuff is excellent. They show you code samples of exactly how you make the call to send the image to the system and how to get everything back. So really easy to do. You guys guys and gals have all done RESTful API calls, I'm sure, so no worries there. And the last thing I want to show you, let me just do a little bit of setup. So originally I was going to show you a full demo doing essentially the MNIST detection of deep neural network for numbers. These are characters and stuff like that. But it takes too long to go through it, so I'm just going to show you something that you might find quicker and more interesting, which is essentially it's something called TensorFlow Playground. Now, if you're trying to understand how these algorithms are working, this is a really good visual explanation for what's going on. So we've got an input image. We've got two different, not an image, I should clarify, a two-dimensional data set. So we've got these things that are orange, and these things that you can imagine this is yes or no, or you can imagine that this is a cat and this is a dog, and these are like the length of their ears and their nose or something like that. And so we feed the data into the input, and then we've got a single layer of neurons, and then we've got our output neurons here, and then our predictions. So when we train this neural network, we'll see that this is an easy problem to solve. We essentially just draw a boundary dividing this stuff down here and this blue stuff up here. So that's really, really simple. And we've got more complex patterns that we can then use a neural network in order to classify. So you can see after a few iterations, it eventually starts to tease out that we can get most of these blue ones if we draw a line that way, and then most of the orange ones. And now over time, it's eventually even getting better at its prediction capabilities by bending this line inward. But if we want to make this solve more complex problems, we'll try something like this. A single layer of neural networks isn't going to do very well in this pattern because this is a relatively complex function that generates these spirally intertwined positive and negative test cases. So it's essentially just drawing a line straight in the middle because that's all the complexity it can model. But we can essentially create multiple layers. Whoops, sorry. Let me add the layers first. We can essentially create multiple layers to this neural network to make this a deep neural network. And we can also add additional neurons for each hidden layer as well, too. We're just going to bump this up to 8. So now the complexity of the function we're going to be able to model is significantly greater than the complexity that we are able to model with the much simpler deep neural network. We're going to add additional inputs as well, too. So these inputs are essentially just different mathematical transformations, convolutions, if you will, to the original input image. All right, so now we got this super deep, it's not really super deep, but a deep neural network that has significantly more neurons per hidden layer, and we're going to rerun this to see if it can essentially predict this function. This is going to run for a little while because obviously this takes quite a bit more CPU time in order to model. But you can see it's eventually trying to converge on a set of boundaries, or essentially ways to divide this space of data in order to increase its prediction capabilities, minimize its error rate as much as possible. And as you can see, it'll go through several iterations, and it's kind of oscillating now, but it's starting to learn how to model this function, the function that generated those data, in a way that I think is much easier to understand than just reading a bunch of calculus and linear algebra in a textbook. But hopefully that kind of helps you to understand what's going on. Okay, so we've got just enough time here in order to finish things up and maybe ask a few questions if you're interested in that. So flip back here. All right. It was actually showing the demo the entire time, right? I just turned around and saw a blank screen. Okay, just because if nobody called me out on that, that was really awkward. Okay, so where do we go from here? Like, if you're interested in learning more about this deep learning stuff, like, where do you even begin, or where do you get started after this? All right, so I think there's 3 paths that I generally recommend to people based upon your background and experience and what you're trying to get out of this. So first, if you're kind of new to programming or new to R and Python, DataCamp, I think, is the best place for you to go. DataCamp essentially is an interactive programming website that teaches you how to code in R and Python and works you all the way from data science up through machine learning and into deep learning as well. They've got some pretty decent deep learning courses on there. But if you already are a pretty experienced programmer, you know your stuff, or you know Python and you know R, you might just want to go straight to Pluralsight. Pluralsight's more pragmatic. It's essentially, I just need to know the things I need to know to start using this on Monday at work kind of approach. I already know how to program. I just want to learn deep learning. Really good courses on Pluralsight as well. Several of them belong to me. There's also Coursera, which is more academic in nature. So if you really want to get in deep and learn how deep learning works from the ground up because you have a background in calculus and linear algebra, and you really want to understand this so you can build your own algorithms from scratch, Coursera is probably the place to go. As I mentioned, I have several courses on Pluralsight that you might find interesting. So Deep Learning, the Big Picture, covers what we covered here today, but actually goes quite a bit more in depth. Data Science, the Big Picture, goes to the entire overarching landscape of data science. Then we've got Data Science with R, Exploratory Data Analysis with R, and a 3-part data visualization series as well, too. Finally, be sure to use me and my website as a resource as well. I've got all of the slides for this presentation, videos, articles, full-day workshops, open source software, you name it, on this topic and more. Quite a bit of information there. And finally, before we wrap things up, feedback's very important to me. Like, I use your feedback to improve each and every one of my presentations I give. So if you come and talk to me afterwards, just let me know one thing that you found valuable about this presentation and one thing that you think I could do to improve. I promise you this stuff helps me way more than the quantitative metrics when you guys are submitting your feedback with a like or a frowny face or whatever on websites. And I promise you will not hurt my feelings. I really value good critical feedback. All right, so in conclusion, today, we answered 3 questions. We learned what deep learning is, we learned what deep learning can do for you, and we learned how to get started with deep learning. Now, I really believe that we're just beginning to see the beginnings of this artificial intelligence and machine learning stuff in our industry. Deep learning is going to have a fundamental and profound impact on software and the IT industry for many years to come. So, to end, I'd like to propose 3 new questions to you. Are you prepared for this? Is your organization prepared for this? And is our world prepared for this? If you, your team, or your organization would like help beginning to transition into the deep learning era, please reach out to me. I would love to help. Thank you very much. All right, so it looks like we've got about 2 minutes and 30 seconds left. Does anyone have any questions they would like answered? I would be happy to. Yes?
So you talked about society not being ready for this.
Yes.
How about the legal aspects of it? And I'm thinking in the U.S., racial profiling or making sure mortgages don't get biased towards a certain group or not. Those are all regulatory things.
Yep.
This blows,
Yeah. So this is something that we really need to be wrestling, and nobody's prepared to even discuss it at this point in time, especially our politicians. They're just not ready to have these discussions. But this is going to be huge. So with deep learning, one of the most important things is transparency. So we've got things like decision tree classifiers that are really simple and easy to understand. And then on the other end of the spectrum, we've got deep neural networks, which are ridiculously complicated. You can show a decision tree classifier's decision-making process to a judge, and the judge will say, yes, I understand why it made this decision. No, you did not racially or whatever discriminate against this person when you approved or denied their loan. Deep neural network, you show that to a judge, he's going to be, I have no idea what this thing, like why it made this prediction. And then he'll ask the developers, why did it make the prediction? They'll say, we have no idea either. It's just a black box. We feed it data and it gives us answers and we make money. So this is a big problem. There are people working on it. The overall like technical details of the legalese and stuff I can't really go into, but what I can say is that the best potential solution to this I've seen so far involves, say for example, you're doing diagnostics for cancer treatment. You feed in images of melanomas on the skin, and it says whether, you know, like a human doctor says this one was cancer, this one was not, this one was cancer, this was not. So it does the predictions really well, but what we also do then is have the human doctor type in a description of why he said it was cancer. Well, it's got raised edges, blah, blah, blah. The color was, you know, transfused, blah, 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 something like that. And we can do textual analysis in addition to that deep learning analysis. So not only are we able to predict the output, but we can also then generate or synthesize a textual explanation for why it made the decision that it did based on doing that textual analysis, just like we saw with the image descriptions. And the combination of those two things right now are the best thing we've got for trying to explain why a deep neural network made the decision that it did. Yeah.
Okay, so you missed the diagnosis. Who gets the malpractice?
My guess is in the near future, doctors will have a consult with an AI system, and if the two are in agreement, they'll move ahead with the procedure. If they disagree, they'll pull in a third human doctor to essentially tie break. But who knows what it's going to look like. Yeah, it's a really big can of worms, and it's coming fast. So, one more question? Nope, time's up. All right, well, thank you very much, everyone. Have a great day.